Welcome back to my system design series where we break down the complex system design topics into simple, relatable, and actionable knowledge. If you are new here, I am Achi Gandhi, and today we are going to dive into something that powers some of the world's fastest databases, a data structure called LSM or log structure merge trees. Now, I know that you are thinking that another data structure, how it is different from others. Well, here is the thing. If you ever wonder how millions of writes are happening per second without breaking a sweat, then understanding LSM trees will be very helpful. Okay, so what do you mean by LSM trees or log structure merge trees? LSM trees is a data structure used in NoSQL databases designed to manage writes efficiently by combining MemTable, SSTable, that is a sorted string table, and compaction. The key idea behind the LSM trees is to optimize write performance by using append only writes, followed by periodic merging of data, which is called compaction, to the disk. The tree itself consists of multiple levels of SS tables, with each level getting larger as data is flushed from memory to disk. Okay, so let's talk about the structure of LSM tree. So first is MemTable. It is in memory data. So just imagine that number of write requests are coming, and this is our MemTable. So it is of a specific size. So let's take it like, suppose this is the size and this is the another block. So once this whole block will be filled, then write entries will start filling into this block, and after that it will be flushed. Once the whole block is filled with the write or with the data, it will be flushed into this disk, that is a SS table or sorted string table. It could be even the hard disk. So this mem table is storing the data as key value pair. So you have heard about the red black tree, right? So it is the similar structure. Suppose this block is full with the data. For example, 101 is Ria, 102 is, let's say, Archie. So it is now flushed into this disk. Okay, so this is the second, that is a SST. Now, what is the speciality of this thing is that it is a, okay, let me write from, okay, immutable. That means once written, it won't be deleted and you can't even update this. So here how the data is stored in the form of levels. For example, this first block is full, right? So it is flushed in this like this, and then the second block will be flushed like this. This is the first, this is the second, and this is the first, this is the second block. So this is the level 0, this is the level 1. So let's talk about the fourth part, that is a compaction. So compaction is the process of merging SS tables across each level. So for example, this block, the block first, was having 101 Ria and 102 as RG. Now suppose there's another block which is of bigger size, and it was having 103 as Simran, and again 105 as Archie, and 101. Now this will be combined and all the repeated or duplicated data will be removed and merged into one single data. For example, here it would be, as you can see, Arch and Ria are repeated. So 103 will be of Simran, then 105 will be Archie, and 101 will be Ria. So this process removes the redundant data and keeps the system efficient. So we have discussed about the LSM trees. Now let's talk about how to make LSM trees reliable. So for this we are using WAL, that is write ahead log. So every write operation is first written into WAL to ensure durability. This log stores the data on the disk before it is storing into the meme table. So if a crash occurs and the data stored into meme table doesn't exist, then there comes WAL as a handy, which allows the recovery by replaying the log and ensuring no data is lost. So whatever the data, like it is returned with the timestamp and the data. So all the writes are written like this in the sequential manner. So for example, this is the meme table and this is the log like WAL. So here with the timestamp, first the data is entered here. This is the data. Then it will be entered into this the data. Second, suppose the second entry of the data will be written with the timestamp, and here will be the data, and here it will be written after that. And in between, so first data is written, right? And suppose the meme table is crash in between, then after this, again, we can, like collect back the data from this and we can make the meme table again. So the second thing which makes the LSM trees reliable is the compaction, because compaction strategies can be tuned based on the factors like system performance and space efficiency. For example, the system can decide to compact SS tables at specific times. For example, when the database reaches a certain size or during the low usage periods. Third, the most important is bloom filters. So, bloom filters are used in LSM trees to quickly check if the key exists in SS tables, reducing unnecessary reads. But they are not 100% efficient. If, for example, if the bloom filter is searching for the key, suppose 59, and here all the starting points of the keys are mentioned. Suppose this is 43, this is 59, this is suppose 58, and this is 60. And here, so here the starting key is 43, then we can take as 47 and then 60. Here starting key is 58, and then there is a 63, 69, and here there is a 60, 71. So here you can see that first it will check that if it is greater than this particular key, so 43, so yeah, it can go inside and check. And if it is greater than 58, so yes, it can go inside and check. It is greater than 59, but here the starting key is 60. So it won't go inside and say no, it doesn't exist in this particular block. So this bloom filter checks the blocks which are the latest ones. So suppose this is our level 3 and this is the latest block, right? So it first checks inside this block, and especially the first key it will check. So here it is 60 and we are finding 59. So 59 is lesser than 60, so it won't be inside this, because as we have discussed, this are sorted ones. So inside this block all the keys are stored as sorted keys. So we can go into the last second one, that is a level n minus 1, and here the starting key is 58. So here there's a probability that key will be inside it and it might not be there. So here it's an example that bloom filter might not be able to find the key inside this particular block, but it is definitely telling us that when the key is absent. So when the new key is inserted into the SS tables, the bloom filter applies multiple hash functions to this key. Okay. For another point which will make LSM trees reliable is the garbage collection. As SS tables are compacted, outdated data is removed. Garbage collection prevents the system from holding onto outdated SS tables, freeing up storage space that would otherwise will be wasted. So let's talk about the real world use case of LSM trees. So first, it is used in high write workloads in distributed databases. So first is Cassandra, which is scalable NoSQL database. So Cassandra is highly scalable, NoSQL database developed by Apache, which is built to handle high write workloads, making it perfect for the applications such as IoT, logging, and analytics. So every write in the Cassandra first enters into the MemTable and then gets flushed into the SSD disk. With Bloom filters and compaction, Cassandra handles fast writes while keeping the reads efficient. And that's why the companies like Netflix and Instagram rely on Cassandra to process billions of writes every day. Second use case is embedded storage engine. For example, RocksDB, which is used as high performance storage engine. So RocksDB is developed by Facebook, which is an embedded storage engine that powers the applications requiring low latency data access. So it is widely used in systems like financial transactional logs where maintaining the high write throughput is critical. So Facebook itself uses RocksDB for its messaging system and newsfeed storage, handling millions of writes seamlessly. So another use case is real-time search and analytics. Elasticsearch, powered by Apache, uses LSM tree principles to index and search the data efficiently. Every time new logs, metrics, or documents are added, Elasticsearch organizes them into immutable segments on disk, similar to SS tables. This enables real time search and analytics for platforms like Slack and e commerce giants like eBay. Another use case is key value store. Another system which is using LSM trees are Google's Level DB, which is ideal for scenarios where a lightweight and fast key value store is needed. For example, Level DB are often embedded in mobile applications for local storage or in backend systems for caching purposes, enabling seamlessly data retrieval without high storage overhead. So, this was all about the LSM trees, and we have explained the structure of LSM trees, its use cases, and everything. So, in the next video, we will compare the B trees and LSM trees. If you have any doubts or any suggestions, please comment down in below. And please subscribe to this channel because it will motivate me to make more videos. Thank you so much for watching. And please make sure you like, comment, and share with your friends who wants to understand system design topics into very simple manner. And thank you so much for watching.